Good morning, everyone. Welcome back for this third day of the conference. For the first talk this morning, I've got the pleasure to introduce Jean-Claude Hausmann from the University of Geneva, who will be talking about the cell dispensability problem for spaces and manifolds.
Okay. Thank you. That works? So I'm not going to talk about anything related to the work of Vaughan Jones, but it's so basic algebraic topology that it should be related in some way. So we consider the following problem. We take a space and we ask whether it is homotopy equivalent to a CW complex without cell in some range. Okay. Le milieu, ça marche pas. Voilà. So I start with a one connected case, which is very classical, but it will give us tools for the general case. So I take a simply connected CW space, means it has a homotopy type of a CW complex and a finite type of a CW complex with finite skeleta. And so take this definition, KL cell-free. If it is homotopy equivalent to a CW complex with finite skeleta and without cells in this range. It's not the same as saying that it is homotopy equivalent to it is a finite type, homotopy equivalent to something with finite skeleta, and maybe homotopy equivalent to another complex without cells. So that would be a different problem. I'll comment on that later. I ask the two conditions to be fulfilled with the same complex. Simultaneously. And we try to get some algebraic topology tools for something maybe which is equivalent to that. And for instance, of course, if it is KL cell-free, it has no homology in this range KL because there is no cell. But it's better to use cohomology. It will be more operational. So we say, is this cohomology KL silent? I made up this terminology, so if there are people, English-speaking people, they could, I would appreciate comments on that. So that means the cohomology is 0 in this range for any Z module, so any abelian group R. This is an ad hoc definition for the simply connected case. It will be different afterwards. And it's a very classical theorem that if X is a finite type and simply connected, then the two conditions are equivalent. And as a warming up, I will prove this theorem. So allow me to be elementary for a couple of minutes. So I take a CW complex. It's not a CW space. It's a complex given with this cell decomposition. And we look at the cellular complex to compute the homology. And if it's homology silent in degree Xi, if and only if, actually, but I will I will use the only if part. The inclusion of the boundary, so how do in German, admits a retraction. And second, the homology in dimension degree G is 0. So let's prove that. For I, this is a cellular complex. And the boundary, the image of delta is in, that's the boundaries. And this is the cocycle, that means composed with delta, of course. Delta composed with delta is 0. So that's the definition of the cohomology that would be a cocycle. That means an element in this in the cohomology with respect to these coefficient, to bk minus 1 of a as coefficient. That's a definition of cohomology in a abelian group. And it's a cocycle, then as A is cohomology silent in this degree, that means it's a co-boundary. That means it's this homomorphism factor, and we check that retraction. And for the other one, we notice that, anyway, of course, we are a free abelian group, so we have, this is a subgroup of a free abelian group, so of course it's a free abelian, but we won't use that. It's a bad reason, at least as it is a direct summand, of course it's a stronger reason to be. Anyway, this would then split, and ck of A is zk, the cycle plus the boundary. So for the second movement, we have then this isomorphism. Zk goes to the homology, cycle to its homology class. And as it has a direct summand, we can extend this map, for instance, by 0. So that gives a homomorphism from the chain to this abelian group. And again, it's a cocycle, because the boundary goes to 0 to the homology. So then it's a co-boundary. So from the cycle to the homology, it's surjective. But here the cycles go to 0. So the map is surjective and 0. That forces the group, the homology, to be 0. Okay, now we can prove the theorem in the non-trivial direction. Suppose X is cohomology silent. So I take a CW complex of finite type in the homotopy type. I still call it X. And we just saw by the lemma that the chain in dimension k minus 1, the boundaries is a direct summand. So there is a supplementary, which is, of course, Z free. And that's the definition of the chain. And we have the Hurewicz homomorphism. So the pair is K minus 2 connected, I guess. So this is the first non-zero homotopy group. So if K is greater than or equal to 4, the two, why is it? No. The two space here, K minus 2 would be X2. The two spaces are simply connected. So by the Hurewicz isomorphism theorem, it's an isomorphism. So if K equals 3, this is X1. This is not simply connected, but still it's an extension of the Hurewicz theorem. It's still surjective. And so what is a homotopy group? That's good. Yeah. It's a homotopy class of map from dk minus 1 to xk minus 1, sending the sphere to xk minus 2. So maybe I should say what we will do first. We have X, and we start with X minus 2, the 2 skeleton. And what we are going to do is attach cells, K minus 1 cells, in a clever way, so that this inclusion extends. And this map is actually L-connected. So we can get X by adding cells of higher degrees. So this is what I said, pointed homotopy map, class of maps for disk here. So that's actually, we need to attach cells. We can use a small phi to attach a cell to xk minus 2 using this map. And this augmented complex with this new cell, the inclusion will extend to the cell using the map capital phi. So we can do that for, as it is free and finitely generated because, well, X is a finite type, so X has finite skeleton. So we can do that for a basis of Q. So I take the basis of Q. Each element can be represented by an element of the homotopy group, since the map is surjective. So I take these maps. And I attach cell using the at K minus 1 cell using the phi I, capital phi I. And as I said, this inclusion extends to a continuous map using the capital phi. And if we look what this map beta does on homology, well, it's an isomorphism till at least K minus 1. Because in dimension K minus 2 and K minus 1, the homology, the boundary here, this is going to 0 in HK in CK minus 2. So the homology in dimension K minus 2 is influenced only by things coming from Q. And also in dimension K minus 1, that's a cycle of in Q. This doesn't contribute to homology. So finally, and of course, we have done everything. This Hurewicz map, factors through the boundaries and so on. So we have at least, the map is at least K minus 1 connected. But then what the next homology? By the lemma, we prove that this is 0 if it is cohomology silent till L. And of course, Y is K minus 1 dimensional, so it's 0. So the map is highly connected. It is L-connected. And it's very classical that if you have a L-connected map, you can make a homotopy equivalence by adding cells of higher dimension. So that's the proof of the one connected case. Now let's go to the general case. So again, we take connected simple space of finite type. The fundamental group will be denoted by pi everywhere, always. And this is the same definition. But now for the homologic silence, it will be for any z pi module. I maybe comment on that and say exactly what it means. So it's a slightly stronger condition. And we can try to prove the third. Is that equivalent? Well, we first prove the lemma. The lemma is OK. if we have connected CW complex, it's okay, but we have to take the universal covering. So we replace A by its universal covering. The group pi acts by deck transformation, say on the left. And so everything is a Z pi module, a left Z pi module. And the same proof proves that you get a retraction. So this boundary is Z pi projective. And here, the homology is also 0. So the proof is exactly the same as before. I don't this image of delta is a surjective, it's a co-cycle, then it's a co-boundary, and here. In the simply connected, you could use, for instance, to get 2, you can use universal coefficient theorem. But that's not available for local coefficient like that. So this is a more direct. Now, as we have this lemma, we can try to prove the same theorem. Is convergence silent implies cell-free. So remember, so we take one. So X is a CW complex. And in the simply connected case, we had this line, and that was free. So what happens now? We have somehow the same with the universal covering, but this is only finitely generated Z pi projective. So in the simply connected case, we took a basis of Q and attached cells with that basis, and that solved the problem. Here we cannot do that if it is only ZP projective, but if it is ZP free, that would be okay. That would be the same, exactly the same proof. We choose a basis and so on. So if Q is ZP free, it would be okay. It's still okay if it is stably free. Stably free means it becomes free if we add free summands. Because it's free summand in degree k minus 1 that can be obtained by adding trivial k minus 1 cells, making a wedge with k minus 1 disk that would add cells and then add a free summand here. So it's still okay. And here a remark. When you have a projective module, it's always infinitely stably free. Okay, so that's what I said. If it is, if Q or equivalently, because that's the same, it would be the same condition, is Z pi stably free, everything is okay. But Q is infinitely free. If P plus Q equals is free, then Q, say P, Q plus F infinity is F infinity. Is just that's very standard. You take Q plus P plus Q plus P plus Q, and so, and once you bracket that way, which is Q, which makes Q plus F infinity, and if you start the bracket here, you get F infinity. That means the statement of the one connected case would be true if we allow the infinite skeleta. So the space would be of finite type and would have the type of something without cells in the required range, but at the expense to have here another complex which infinite skeleton. But we want to, but we don't want that. We want to keep the finite skeleta, but then we are stuck. the non-stably freeness of the matter is an obstruction to do that. And this non-stably freeness is measured in a K0 tilde. So we get an obstruction called WK of X. So we take the class of these boundaries. In K0 tilde of Z pi, that's exactly the finitely generated projective Z pi module modulo the stably free one. It's an abelian group for the direct sum and so on. Why is this minus 1 to the K? Well, say if you have something which is cohomology silent, say between 10 and 20, so you would have a W10 here as an obstruction. But it's also cohomology silent between, say, 13 and 20. So you would have a W13 and W14 and so on. So if we put this minus 1 to the K, that's the same obstruction. So there is only one obstruction, not one at each degree. And if it is 0, that means it's stably free, and we say the same proof applies. So a connected CW space of finite type, which is cohomology silent in this range, L could be infinity, determines an obstruction. Depending, so we have to work, that's not so easy, to prove that it depends only on the homotopy type of X. So it can be defined for CW space X, because we choose a CW complex and doesn't depend on this choice. And it vanishes if only if X is self-free. People who know about the wall obstruction should find that familiar. Technically, it's a definition of the wall obstruction. If L is infinity, then that means that's a wall obstruction which vanishes if and only if the complex has a homotopy type of a finite complex. But here it's a new use of this wall obstruction for another setting. For instance, you can have a space which is self-free between cohomology silent between 10 and 20, and then between 30 and 40, and then above 50. And so you get three obstructions, W10, W30, W50. And W50 is actually the wall obstruction, if there is. But there is no relationship between these obstructions. And one more line. I stay vague, but we can realize any element of K0 this way by cohomology silent space with pi 1 of the space identified to pi. This is the same level of difficulty. It's a bit delicate, but we construct by adding cells and chasing diagram and so on. It's not more difficult than what I said, but it's a bit long and delicate. So let's go to now the manifold case. So I take a smooth closed manifold. Closed means compact without boundary. And M is called K anti-simple if it admits a Handel decomposition without Handel around the middle of dimension between K and R minus K. And we can take the same cohomology K anti-sample if it is K R minus K silent. So about 45 years ago, before there was the notion of simple manifold. That means it has nothing no handles except around the middle of dimensions. That's simple manifold. And 45 years ago, I introduced this anti-simple manifold, starting to study also complement of high dimension nuts. And then a couple of years later, Shmuel Weinberger and other authors consider the second condition, thinking it's more natural. And they call that anti-simple. And everybody was, I guess, if you know, under the impression that we should have something like a kind of wall obstruction, which measures the difference between the two. But that wasn't done, so I mean, maybe I say it's maybe time for me to do the job. So if it is a cohomology anti-simple, a smooth, a closed manifold has a homotopy type of a finite complex. So this cell dispensibility obstruction is defined. And believe it or not, we have the same theorem if the dimension is at least 6. Anti-sample if and only if this obstruction is 0. It's because if the obstruction is 0, as we saw before, the manifold has a homotopy type of a cell complex which has no cell in the middle of the dimension. And there is a very famous technique introduced by Smale for the H-cobordist theorem and then S-cobordist theorem, which permits to eliminate a handle if it is homotopy. Okay, we can do it geometrically. So modulo Smale theory, it's the same. But remember, at the end of the theorem, I add a line saying that every obstruction can be realized. And here I cannot write this line. So it's a question. And I was surprised, actually, it's rather difficult. First of all, the line cannot be written because it's not true that any obstruction, any element of K0 occurs in obstruction. In fact, there is a necessary condition. So this obstruction, you have this formula. This is the dual. When you have this is the UK of M is represented by a projective, finitely generated Z-pi projective module. We take its dual. Well, technically, we have left modules. The dual would be a right module. So we have to make it a left module by using an involution on the group. Usually the involution comes from G, goes to G minus 1. If the manifold is orientable, otherwise G minus 1 times the orientation character. So we have to I never say the manifold can be non-orientable. So this is because if we have a cell decomposition, and which makes, handle decomposition, which is like a cell decomposition up to homotopy, it gives the obstruction. But we can take then the dual cell decomposition. And if we compute that, we get exactly the two obstructions should be the same because it depends only on the homotopy type. But if we look at formally, they are not the same. One is that, and the other is that. So this should be equal. I say Poincare duality implies that's not true, actually. It's the existence of this dual cell decomposition, which implies Poincare duality, but you could have a Poincare duality space which doesn't satisfy that. So at least we should have this condition. Is that enough? Well, I would call that a self-dual element. R is fixed. And so if the element is self-dual, it defines a class. So we have an involution passing to the dual on that. So it's a Z2 module, and this is a so-called Tate cohomology in this module. Actually, it's just the one which are self-dual modulo the one which are self-dual by trivially, because they are a sum. So we can consider this class. This is a two-group, group of exponents, an abelian group of exponent 2. And it sits in an exact sequence introduced by Andrew Ranicky in 1973, I guess, in his first fat book on algebraic L theory or something. So this sits here. These are the wall group, the wall surgery obstruction group. That's for a surgery problem. We try to, we have Poincaré spaces, Poincaré complex, and maps, some nice maps from a closed manifold to them, and we try to make them cobordant to homotopy equivalence. So this is, we get at some point an obstruction in these groups. This is when the Poincaré complex is finite, and here when it's only finitely dominated. So there is this Ranicky map. And so if we have a self-dual things, and which is in the kernel of this map, then P is really lesable for as a common obstruction, the self-dispensability obstruction for K or cohomology K anti-simple manifold with phenomenal group identified to pi. I wanted to say something. Well, okay. In particular, if the class is 0, it's in the kernel and it's representable. Well, it's not a competent sub. I don't know if this condition is necessary, but it's sufficient. But that's a huge theory that uses ideas of the Siebenmann thesis and the so-called projective surgery of Erik Pedersen and Andrew Ranicky, two colleagues who unfortunately died rather recently. And I wished I could ask them questions, because these are hard things. And I experienced probably probably several branches of the mathematics of the 20th century. The know-how is somehow forgotten. And the new generation have to rediscover and reinvent them. So maybe let's now say about K0 tilde. Maybe not everybody knows about K0 tilde, what we know. Again, it's a couple of 100 pages. So there is a conjecture related to the Farrell-Jones conjecture. This is Lowell-Jones and not Vaughan-Jones. If pi is finitely represented and torsion-free, then this group K0 of Z pi is 0. So that means cohomology silent and cell-free is the same as in the simply connected case. So this conjecture is still open, but it's proven for for many groups, like free abelian, surface group, I guess, hyperbolic, cat zero, etc. Many of these groups by geometric methods. Now, if the group is finite, that's another big theory, but it's mostly arithmetic method, and it can, in many cases, be computed. First, here is a general result. For a finite group, K0 of Z pi is finite. But any torsion could occur. For instance, for symmetric groups. And now if you have a torsion part and some free part or a finite part, it's become very bad. For some of this finite group, if you cross it with the integers, it becomes infinitely generated. It contains Z2 to the infinity. But for us, it's, well, of course, you can maybe realize some of this infinitely many obstruction can be realized, but they cannot be realized starting from a problem with fundamental group pi and cross it with Z1, with S1, for instance. That doesn't work because there is a product formula, which is the same as for the wall obstruction. It is the same proof, essentially. So we take a space of finite type, which is cohomology silent in some range, say 10, 20. And we take a finite auxiliary complex, say of dimension 4. So if we do the product of X with A, it will be cohomology silent in dimension 1420. So again, and with obvious identifications, the obstructions WK plus A is obtained from the obstruction WK by crossing, multiplying with the Euler characteristic of A. So if the Euler characteristic of A is 0, like for the circle, then if you start with something cohomology silent, even with an obstruction, then, of course, here L should be at least K plus 1. Right? Then by crossing with a circle, you erase this obstruction, and it's become cell-free. The same for anti-simple manifold. If you have an anti-simple manifold and you cross it with S1, it becomes, cohomology anti-simple. You cross it with a circle, it becomes anti-simple. So I'm sorry, but I think that's all what I wanted to say. Thank you.
To apologize for being too short. Is there any question either online or on site? I just remind to the online people that they can unmute themselves and speak directly. And anyone on site, please wait for the microphone to arrive. Yes or no?
Could you say why you didn't have dimension 5? I mean, the H-cobordism is also available there, I think. So why did you start in dimension 6?
Well, but what would be the range? Should be below the mandala, so it would be 2. Even for complexes, we started with 3. It may be true, but it requires a peculiar proof.
Thank you.
Any further questions?
Il ne dormait pas.
Say if you have a simple homotopy equivalence, say in the combinatorial category or between CW complex, then you have a sequence of collapse or elementary expansion. Can you use this method to control this something in this sequence?
Good question, but no, I haven't thought about it. Here it's purely homotopy, I don't think. And, well, then you need a finite complexes.
Sure. Yeah. I think the same question could be asked for manifold when you move your critical points by creation, annihilation, and blah, blah. The question is, can you join two Morse functions with certain critical point, avoiding to go with critical points of certain dimension, of certain index?
Well, for anti-simple manifold, they are made like they don't have handles. So you have the lower handles and the upper handles. They have the same homotopy type because, okay, by general position, we can put them. And then in the middle, what can you have? It could be just a double. It could be a double with some diffeomorphism. Or it could be an H-cobordism. And here you have a Whitehead absorption, and you have an analogous long exact sequence, the Rothenberg sequence. I'm not sure I'm going into your question, but okay.
Any other questions? If not, let us thank Jean-Claude again.